All right, so lecture B, we're going to continue with our same example here, where the velocity is 3t squared, which is never negative, so it's also the same as the speed. And t cubed is the distance traveled, also the same as position, since we're starting at position 0. We approximated the area with approximating rectangles, right-hand sums. In the limit as n goes to infinity, as the number of rectangles goes to infinity, and they all get skinnier and skinnier, delta t goes to 0, we get the exact area under the curve. Effectively, it's like we're defining what the exact area is as a limit. But we can also find the exact area, or distance, or position, with the Fundamental Theorem of Calculus. Now, so far we've talked about the Fundamental Theorem of Calculus and what many people think of as its harder form in Chapter 6. It gives two names to, called the Second Fundamental Theorem of Calculus and also the Construction Theorem for Antiderivatives. We did that version first. Here's the easier version, sometimes called the First Fundamental Theorem of Calculus. I think it's worth doing the harder one first. That's why I did it. Let's do some explanations as we go. It says this. Suppose little f is continuous on the interval from a to b, and suppose that capital F is an antiderivative of little f on that same interval. In other words, capital F prime of t always equals little f of t for all t in the interval. Then the integral, the definite integral of little f of t from a to b can be computed very easily as just doing the difference of these two function values. You don't have to do Riemann sums and figure out what the Riemann sum equals and then let n go to infinity, in many situations at least. There are hard situations where this is not so helpful. It's always true, it's just not always helpful, as we will see more on Friday. It's pretty amazing. Do the integral, find the area, or the signed area if the graph goes negative, by doing a difference. This is definitely a useful thing if you can figure out what capital F is. If you can figure out an antiderivative for little f. Now realize I'm doing a switcheroo on you as far as notation goes. If I'm going to relate this to the velocity example, little f of t now actually would represent the velocity. Thinking about that example, it'd be better to say we're integrating v of t instead of f of t. And I'm using a capital F. Where'd that come from? Well, I just made it up. It's a common thing to use. I'm not bucking, it's tradition. I'm not bucking tradition. But in this context, the antiderivative would actually be the little f. Another way to write this would be the integral from a to b of f prime of t dt. Little f prime is little f of b minus little f of a. These equations, in the context of the position and velocity, mean the same thing as that equation, just changing how the letters are used. The v corresponds to the little f corresponds to the capital F, little f prime also corresponds to the little f here. This is the more traditional way to write it. And it applies to situations where the variable's something else, like x. If I write the integral from a to b of f of x dx, that's also going to be capital F of b minus capital F of a. It really doesn't matter what the variable name is as far as the integral is concerned. It does matter as far as your intuition about the application. Either way you think of it, you're still finding the area under the graph, if the graph is above the axis, or the signed area that goes below. We talked about in lecture 31b. So for the problem at hand, this feels circular. It feels like we're going around in circles. The velocity is 3t squared, and the antiderivative is t cubed. Therefore, the total distance, which also equals the change in position, which also equals the position itself if we start at position 0, is found by doing this difference. And there we go, 8. So if you can find an antiderivative, this is saying you can find the area easily. But that is a catch. There are plenty of situations where you can't find the antiderivative. Formula is just too difficult, too complicated. Or maybe a standard formula doesn't even exist. And so we start finding new functions that you've never heard of. Like what we see before, elliptic f or something like that. Elliptic functions, they're called, are some examples. There are hundreds of other examples of functions you've never heard of before this class that people have defined and computed approximate values for using technology for capital F, but you can't find a simple formula for it. So in some situations, you have to approximate the answer. You've got to use the rectangles. And maybe you just have to do an approximation because the limit as n goes to infinity is too hard to figure out. There are plenty of situations like that. Plenty of important applications where that happens. So this is always true, but it's not always helpful. It's still fundamental. It's still really important. Actually, in this last calculation, any antiderivative will work, just like it was mentioned in the 3 blue 1 brown video. You could put a plus c in there, it doesn't matter, because the c is going to cancel anyway. If c were non-zero, it would no longer be the position function, but as far as evaluating the integral to find the answer to be 8, the c doesn't matter because you end up canceling the c's anyway. C minus c, 0. So when you're doing that kind of integral, c can be anything. Usually people just pick c to be 0 when they do the integral. Why bother? Get that? A lot of content here today. Gotta think about it. Let's go back to parametric curves. I got to go even faster here. This is going to include some new ideas and some review. This is from lecture 30. Remember this one? Lecture 30, when was that? Was that before Thanksgiving? Yeah. Remember that one? Nice, pretty picture. We had a graph like this where we were talking about the speed and distance traveled. We started at time -2. Why? Because we can, if we feel like it. It's not the most natural thing to do in most applications, but as far as the math goes, we certainly can. And it does have the benefit in this picture of making the picture nice and symmetric. I'm down here when t is -2, and the motion, bug walking on a table, or maybe this is a picture of a parking lot and you're driving your car or riding your bicycle like that. And these dots are in equally spaced moments in time. This is t equals -2, t equals -1.75, -1.5, -1.25, -1, -0.75, etc. We keep letting t go up by 0.25 here. When the dots are far apart, that means you must be moving fast. The speed is fast. Like this red graph here is high. When they're closer together, you're moving slower. The red graph is low. Then they move further apart, you're moving faster again as t goes toward 2. The distance traveled, now I am talking distance, not position, goes up fast at first, high slope, because the speed is high. Speed is the derivative of the position. Then it gets closer to 0 again because the speed is low. Then it gets higher again in slope because the speed is higher in value. The slope of the blue curve, the slope of this red line, is the value of the red curve at that time. The area under the speed curve is the value of the distance curve, second coordinate there at that moment in time. at this in Mathematica. Again, I'm not going to test you on this kind of Mathematica stuff. There's the graph of the parametric curve. Here I decided to make a manipulate showing the motion. Goes fast at first, slows down, then speeds up. I can also introduce some vectors into the picture. I'm not going to test you on vectors, okay? I just want to introduce them to you. They're really important in physics. And they really make the pictures come even more alive. You see two arrows here, a blue arrow and a red arrow. The blue arrow is based at the origin, though when it's close to the origin, it's hard to tell that it is. It's a little bit misleading the way it looks. And its tip is at the location of the object as it moves. It's called a position vector, a two-dimensional position vector. There are also three-dimensional position vectors if you've got a bug flying through space, or a spaceship going through space, or the Earth going around the sun. What's the red arrow? The red vector. It's a velocity vector. Notice it's always tangent to the curve. It's at any moment in time pointing in the direction of the motion. And it changes length. It's longer when the motion's faster and shorter when the motion's slower. And in fact, that velocity vector, that red vector, is actually the derivative of the position vector. It's the derivative of the blue vector somehow, in a way I'm not going to make clear. It is somehow measuring how fast the blue one is changing, both in length and direction. I'm not going to get into details. I can also add an acceleration vector to the picture. Now it's a third vector, kind of a pinkish color there, technically magenta in Mathematica. That's the acceleration vector. What in the world? Yeah, it's the derivative of the velocity vector. It's somehow measuring the rate of change of the red vector. How? Well, one thing I want you to notice is that when the angle between the red and pink vectors is large, like it is at the start right now, bigger than 90 degrees, the red vector is getting shorter. And when the angle between the pink and red vectors is small, like now, the red vector is getting longer. That's one relationship. Something else important here is that the pink vector is related to the total force on the object because of Newton's second law. F equals ma can be written in vector form. The little half arrows that I put above these symbols represents a vector. Some people put full arrows. In fact, on the PowerPoint, I've got full arrows. The force, the net force on the object as it moves is its mass times its acceleration. A scalar multiple of the acceleration is the force, meaning the force, the net force on the object as it moves is parallel to that pink vector and is proportional to its length with proportionality constant equal to the mass. That tells you what the net force is on, say, the car as it moves without having to think about any details about forces like friction and so forth. That's really nice. As long as you know the motion, you can figure out the force, net force, total force, without thinking about, again, forces like friction and so forth that get real confusing. That's a really nice thing. You can write the position vector like that and the velocity vector like this. Here I have the PowerPoint, put full arrows above the letters. You see some funny looking things in there? You see an I hat and a J hat? The book briefly describes I hat and J hat in section 4.8. I hat is a vector that points directly to the right and has a length of 1. J hat is a vector that points directly up and has a length of 1. The lengths of these things equals 1. Any arbitrary vector, say like this, can be written as some multiple of I hat. I hat is this vector here, plus effectively some multiple of J hat. It's very similar to how we assign coordinates to points in a rectangular coordinate system, except we're not thinking about points, we're thinking about arrows. I don't want to get into details. I'm not going to test you on this, but I just want to introduce you to it. To find the velocity vector, you just differentiate each part of the position vector, the f and the g. And draw these things as arrows. It's best to put the position vector to start at the origin, because then its tip will be at the location of the object. It's best to put the velocity vector to start at the location of the object, because then it points tangent to the curve. And the acceleration vector can be found with a second group. This has more relevance to you if you're a physics or engineering. Okay? But even if you're not physics or engineering, it's still worth learning the basics. And I'm really just introducing them to you. It'll be helpful for us on Friday, because we'll talk about projectile motion. It'll help us understand that better. So that's why I'm briefly introducing it, but I'm not going to test you. 11 minutes, okay. Again, I gotta go fast. Here I want to do a few new things and then review. This slide is about new things. We can ask and try to answer questions like, when is the motion horizontal? In other words, the tangent is horizontal. When is it vertical? When is the tangent going to the curve vertical? Draw a picture on the board here of that parametric curve, and over here. Actually, let me put it over here. It's kind of closer to the computer. Do Mathematica as well. So the curve itself will look like this. Not a very good drawing, but basic idea. The motion was like this. The motion's horizontal at this point, where the tangent to the curve is horizontal. Though it would be leftward motion, the velocity vector points to the left. It's also horizontal down here, where the tangent is again horizontal, though the motion is now to the right. It was vertical right there, where the tangent line is vertical. Slope is undefined, but it's still a vertical tangent. There the motion was downward. It went like this. How do you figure out where the motion is horizontal? I'm talking about this because I am going to assign a few problems to section 4.8 about it. You've been reading about this. Well, the tangent is going to be horizontal when dy dx is 0. The slope of the tangent line is 0. That's actually equivalent to dy dt being 0. The derivative of the motion in the y direction is 0. At this instant in time right here, the motion is horizontal. There's no vertical component to the velocity vector. There's no vertical motion at that moment in time. dy dt is 0. Y was g prime of t, or it was g of t. So dy dt is g prime of t. That ends up being 3t squared minus 1, which you can solve for t to be plus or minus 1 over root 3, which is approximately plus or minus 0.577. You'll be here when t is negative 0.577. And you'll be down here when t is positive 0.577. The motion is vertical. Well, the coordinates of those points can be found by plugging that t into the two functions f and g. So there's the answer. I'll leave it to you to check that. There's a missing thing in here. Right there, there's supposed to be a minus plus in front of it. Not a plus or minus, but a minus or plus. Because when you plug in plus 1 over root 3, you actually get a minus 2 over 3 root 3. And when you plug in minus 1 over root 3, you get a plus 2 over 3 root 3 there. This is really meant to be minus plus. But those are the coordinates, the x and y coordinates of these 2 points. Just plug them into these functions. Plug in the t values into those functions. As far as vertical motion goes, dx dt has to be 0. Ignore this at first. Dx dt has to be 0. Meaning f prime of t is 0. F of t was t squared, so f prime of t is 2t. That's 0 when t is 0. You got vertical motion right here. T is 0 right there, and you're at the origin right there. F of 0 and g of 0 were both 0. That also happens to be equivalent to dx dy equals 0, not dy dx. I'll let you think about that. It's not a typo. And the corresponding coordinate is just the origin. So I'm going to give you a few problems in 4.8 about this to work on. I also wanted to briefly review optimization on closed intervals. So this is repeat. In fact, I quizzed you about this before. It's related to the extreme value theorem, which I'm reviewing as well. If f is continuous on a closed interval from a to b, nothing about differentiability there, just continuity. Then there are numbers c and d in the interval where f of c is always less than or equal to f of t, is always less than or equal to f of d for all t in the interval. In other words, f of c is the global min value of the function, and f of d is the global max value. Emphasis on the word global. And what we've talked about in the past briefly, we didn't spend a ton of time on it, is that to maximize a function over a closed interval, you take the derivative, set it equal to 0, solve for t, to get the critical points. Those give you local maxes and mins by the first or second derivative test. But to see whether they're global maxes or mins, you also have to compare the output of the function at those points with the values of the endpoints. The global max and mins can occur either at the critical points or at the endpoints. That was a quiz question. It was in section 4.1 and 4.2. So to find the global extreme values here, I picked the interval from 1/4 to 2 for a reason. I'll explain why. Square the speed, because it's easier to differentiate that. Set that equal to 0, that derivative. Solve for t, you get 0 and plus or minus 1/3. We did this calculation before, a few lectures ago, when we were trying to find local extreme points. Of what? It's the same example here. Here was the graph of that speed function that looked like this. Now I'm thinking about global extreme points over a closed interval. And the interval happens to be 1/4 to 2. There was a local min at 1/3, just like there's a critical point at 1/3. There was also a local max at 0 and a local min at negative 1/3. We did that 2 or 3 lectures. But now I need to find the global max over this interval. So I also need to not only look at the function value at the critical point, but also the endpoints. And see which gives you the biggest and smallest answers. And notice I'm plugging them back into the speed, not the squared speed. So I need the square root. The biggest of these numbers is the last one, close to 11.7. The smallest is 0.943. On this interval, the high point is right there, the low point is right there. The high point happens to occur at the right endpoint. The low point happens to occur at that local min. The local min is also a global min. So this was just meant to be a brief review of that. It is something you should know for exam theory. I'm not going to take that time to write the answers on the board. There's your global max value, emphasis on the word value. It occurs at the right endpoint, t equals 2. There's your global min value, it occurs at the critical point, t is 1/3. The picture helps you see what's going on. Last thing I want to show you today, that was the final slide, is just a Mathematica animation to introduce the idea of applying this stuff to flows and flow rates. And I think we can get a little introduction on this in 2 minutes. This is going to remind you of lecture 1 a little bit. Except I'm not making the picture three-dimensional. I got a tank of water. Blue water? Yeah, blue water. Right, my painting teacher was wrong. That's extreme blue water, though. What is this? Red water? Don't worry about the colors. Okay, I'm not trying to be literal here with the colors. What we've got here is a tank with an inflow and an outflow. Water can come in, water can go out. The volume, you can imagine this as being three-dimensional if you want, can go up or down. Water is evidently going out right now. Evidently the volume is going down right now. Though I haven't animated anything yet. The blue graph is the volume. The red graph is its rate of change, a flow rate. The flow itself is the water coming in and out. The flow rate is how fast it's going in and out. All we've talked about with integrals applies. But you have to modify your interpretation. You see the blue dot going up and down just as the amount of liquid goes up and down. The blue graph is the volume, say. Imagine the picture to be three-dimensional. The red graph is its derivative. Look, the slope of the blue graph is negative over here, just the value of the red is negative. The slope is positive in here, just like the value of the red is positive. Over here the slope is negative, the value of the red is negative. Here it's positive, the value of the red is positive. The red is the derivative of the blue. It's the flow rate. Units would be like liters per minute for the flow rate. The blue's units would be liters. Times in minutes. You can recover the blue graph, the volume, from its flow rate by calculating the signed area. Though, signed area is really giving you change in the volume, not the actual volume itself. Because the actual volume itself is not starting out at 0. It's starting out close to 4.5 or something. If I stop the animation, say right here, the change in the blue graph, which is negative, it goes down, is the negative of this area. It's a negatively assigned area because the graph is below the axis. When time is right in there, the change in the volume from the starting moment in time is this vertical distance there. That's this area as a positive area minus this area. Minus that area as a positive area. This area minus that area. It's still negative because this area is so much bigger than this one. Here you can see the blue graph's second coordinate for the volume is higher than the starting volume. The net change has been positive over this amount of time. this area, plus this area, plus this area, minus this area, minus this area, minus this area, minus this area, is actually a positive number, because this area is so big. The change in the volume is positive over that time. Okay? All this stuff applies to many situations.
Every day.